Now that we understand something about how to convert an analog signal into a discrete time signal or digital signal, we want to take a look at the reverse process, and that is, if we have a digital signal, how do we reconstruct the analog signal from it? And that's called signal reconstruction. So the first thing we're going to look at is digital to analog conversion. So think about, in the ideal case, that we have the discrete time samples of a signal, and we can, at least ideally, recover the impulse sampled signal from that at the output of a D-to-A converter, for instance. But how do we get that original signal x of t, in this case it's the green line here, how do we get that from just those samples? And really what we're talking about is we have to find a way to fill in the gaps between these impulses. So what goes on in the space in between? And from a more technical perspective, effectively what we have to do is interpolate. So all we have is those amplitude values at individual points at our sampling instance, TS, 2TS, 3TS, and we need to interpolate in between. And that usually implies some sort of polynomial fit between the data points. So we'll first talk about zero order hold interpolation. And effectively what we're doing is whatever the sample value is at a certain instant of time, right here for instance, what we're going to do is actually hold that value constant until the next sample comes up. And then we'll change the amplitude but hold it constant again. And effectively what we get is a staircase approximation to the original signal x of t. In this case, those interpolations are done using horizontal lines. In other words, we're using polynomials of order 0 because we're just keeping the value constant for a certain time. Now, if we think about what's happening from the system perspective and the actual system that we can use to do this, we're assuming that we start with our sampled signal, those impulses, and then we're passing it through a filter. And if you think about each impulse at the input of the filter should be creating a box pulse at the output of the filter. And so the impulse response of the zero order hold filter is a pulse of width Ts. And I've shown that mathematically here, graphically here, and that's called the zero order hold reconstruction filter. It's the simplest reconstruction filter we could use. And what do we get at the output? Well, we have the convolution of that zero order hold impulse response with the impulse sampled signal. And we know that convolution in the time domain means multiplication in the frequency domain, and the Fourier transform or transfer function of that pulse signal is a sinc function. So I just multiply those two signals together. Remember, this is the spectrum of our sampled signal. So now we want to take a look at what happens if we use first order hold. So in this case, we're assuming that there are straight lines between samples. Interpolation with straight lines means polynomials of order 1. And if we take a look at the system perspective of that, we're starting with our sampled signal, and then the first order hold reconstruction filter is actually a triangle instead of a square pulse. And effectively what your signal looks like is that, and we end up with these little straight line segments. Again, we have convolution in the time domain, so we get multiplication in the frequency domain. So let's compare those in the frequency domain. So the zero order hold reconstruction filter starts with the spectrum of the sampled signal, and then we're multiplying it with the spectrum of the zero order hold filter. Remember, it was a sinc function, and this is what we recover. With the first order hold, the sampled signal spectrum is the same. The filter function is different. It's a sinc squared instead of just a sinc. And this is the recovered signal at the output. Now, remember that we're looking for perfect reconstruction, so ideally we would only have that lowest order copy of the spectrum. The zero order hole does get that, but there are some ripples on the side. The first order hole does get that, and there are also some ripples on the side. But if you take a look at the ripples on the side of the reconstructed signal, in the zero order hold case, those ripples are actually a fair bit larger than the ones in the first order hold. So that means we have a worse reconstruction with zero order than we do with first order, which makes sense because it's the lowest order approximation or lowest order interpolation we could do. But Nyquist tells us that we should be able to perfectly reconstruct that original signal if we sampled at a Nyquist rate or higher and if the original signal was band limited. So what type of interpolation would allow us to do that? Well, take a look at the spectrum of the sampled signal again. Effectively, if we had a perfect low-pass filter, then we should get perfect reconstruction. But in the time domain, if in the frequency domain we have a pulse, then in the time domain that means the impulse response of the perfect reconstruction filter is a sinc function. So if these are the samples that we send into the reconstruction filter, remember it's just a bunch of impulses, and then those are convolved with a sinc function, then the output is a bunch of scaled and shifted sinc functions. Well, let's take a look at, or think about that a little bit more. Consider what happens to this. This shouldn't be x of s, this should be x of r. But let's consider what happens for this reconstructed signal at instance t equal to k times ts. Well, at those instants, we just get this for our expression, and note that that sinc function is actually 0 for integer values. And it's only going to be 1 when that integer is 0. So those actually happen to land right on the zero crossings of the sinc function, or that time lands on the zero crossings of the sinc function. And so at those sample points, we get perfect reconstruction for sure. But in between, we actually have the non-zero sinc functions, and what this is telling us is that the additive combination of those actually recreates the original signal perfectly. So the output is equal to the original sampled signal at all sample points, but it's also perfectly reconstructed in between, and it's those added sinc functions that do that. Remember that this is only true for band-limited signals and as long as we have sampled at the Nyquist rate or higher.